Alright, so these are the first 20 elements in the periodic table. Of course, this is block S, this is block P, this is block D, and this is block F. And if I have 4 blocks in the periodic table, please note that these particular guys I'm putting here are just the first 20 elements in the periodic table. Alright, so these are the first 20 elements in the periodic table. Of course, this is block S, this is block P, this is block D, and this is block F. And if I have 4 blocks in the periodic table, please note that these particular guys I'm putting here are just the first 20 elements in the periodic table. But you see, for different levels of learning, especially for O levels and maybe A levels, a lot of students often get confused with the trends of the characteristics of elements in the periodic table. Who are those trends? You have atomic radius, you have electronegativity, you have electropositivity, also known as metallic character, you also have ionization energy, electron affinity, and all the rest. Now, just to help you with a shortcut for knowing the trends of these guys in the periodic table, I developed a shortcut called Gamma is equal to I squared E squared. Now, what does that mean is equal to I squared E squared means? It means that Gamma, please follow me very well, is equal to I-E-E. Now, please follow me. Once you can know this thing, you have known it for life. Alright, so what is D? D means decrease across the period. And who are those guys? You have atomic radius, you have metallic character. Now, this metallic character is also known as electropositivity, of course. The character of a metal is the ability of that particular metal to donate electrons for bonding. So, if you are not donating electrons, you don't have metallic character, that is, you are not electropositive. So, metallic character also means metallicity or electropositivity. Why the last I here stands for ionic radius, please note that this I is not ionization energy but ionic radius. We go to the other side. This I here stands for increase across the period. And who are those guys that increase across the period? You have ionization energy, of course, electron affinity, and electronegativity. Now, so it means that, of course, if this is your periodic table, the vertical relationship between elements in the periodic table is that they have the same number of electrons in their outermost shell. While the horizontal relationship between elements is that they have the same number of shells. Of course, there's a third relationship, they call it diagonal relationship, which occurs mostly between the first member of the group and the second member of the other group. Okay, so looking at these guys, note that the people that decrease across the period are atomic radius, metallic character, and ionic radius. While those that increase across the period are ionization energy, electron affinity, and electronegativity. Please do not forget that Gamma is equal to I squared E squared. And whatever trend that decreases across the period must increase down the group, and any trend that increases across the period must always decrease down the group. Alright, so I have it that who are those guys that decrease across the period? Atomic radius, metallic character, and ionic radius. Who are those that increase across the period? They are ionization energy, electron affinity, and electronegativity. Remember that if you decrease across the period, you will increase down the group. And if you increase across the period, you will decrease the follow me. If you decrease across the period, you will increase down the group. If you increase across the period, you will decrease down the group. Now please, this man called ionization energy for A levels. Alright, there's an anomaly of ionization energy for A levels. I just want to mention this because I'm not going deeply into explaining each of these characteristics. Okay, that ionization energy is the energy absorbed when an electron is removed from a gaseous atom. Or you say the energy required to remove an electron from a gaseous atom, that's called ionization energy. Now, it is meant to increase across the period, but there's an anomaly between group 2 and 3 and between group 5 and 6. What do I mean? If I have the first member of the group 2 family, that is beryllium, having a proton number of 4, and boron having a proton number of 5, the electronic configuration for beryllium is 1s2, 2s2. Meaning that in the outermost shell of beryllium, I have just one box here with a completely fused S shell. But boron is 1s2, 2s2, 2p1. As it stands like this, it means that in the outermost shell of boron, I have this as completely filled, but the p subshell has just one in one of the degenerate cells of the p. So if I am having just one electron in the degenerate cell of p, it still has 5 electrons more to go to be completely filled and be stable. So it is easy to remove electrons from boron than to remove electrons from beryllium. Now, that ease of release of electron in boron makes the ionization energy of boron lower than that of beryllium. Therefore, ionization energy of beryllium is higher than that of boron. It is easier to remove from boron than to remove from beryllium. So, but then, this one says that increase across the period, ionization energy is supposed to increase across the period. Now, if ionization energy is increasing across the period from between group 2 and group 3, it does not increase, but rather it decreases. Okay? It also happens between group 5 and group 6. Group 5 and 6, example is nitrogen and maybe oxygen. This is 7 and this guy is 8. Alright, this is 1s2, 2s2 and 2p3. This is 1s2, 2s2 and 2p4. Writing the degeneracy for S block. S block is just one fold and this one is 3 fold. Now, if this guy is completely filled, obeying Horn's rule, you have to fill singly before pairing. Okay? In the outermost of the oxygen, I also have it that my S is fully filled, but my P is half filled and has an extra one. If you want to remove electron from either nitrogen or oxygen, it is easier to do from oxygen, because the most stable state of any orbital is the fully filled state. The next most stable state is the half filled state. So if you found out that nitrogen is already half filled, oxygen is one above half filled, it is easier to move from oxygen to become half filled than to move from nitrogen that is already half filled. Of course, so the ionization energy of oxygen is lower than that of nitrogen. But according to my trend, ionization energy is supposed to increase across the period. But that of nitrogen will be higher than that of oxygen. So please note that the ionization energy increases across the period, but between group 2 and 3, there's an anomaly. And between group 5 and 6. Remember that how do you know this again? That V is equal to I squared E squared. And let's go over that again. Who I put that decrease across the period, atomic radius, metallic character, and ionic radius. Who I put that increase across the period, ionization energy, electron affinity, and electronegativity. Remember that if you decrease across the period, you will increase down the group. If you increase across the period, you will decrease down the group. Please like, share, follow, and subscribe. I'll see you some other time. My name, the Pajo.